Welcome back to physical chemistry. Now we're going to try to connect those things together. So last time we talked about how energy levels are populated from the bottom to the top as we heat up, or we can have direct jumps if we shine in light. So this picture behind me is of hydrogen. It's a graph of the specific heat capacity, which is how much we have to heat something up to make it go up by 1 degree in Kelvin in this case. It has 3 steps on it, and that is real. If we measure hydrogen, H2, we can see these steps. So what is going on? At the low temperature, all of the energy is going into moving the particles around, so it gets hotter and hotter, and so it just depends on the mass of the particles and how much we've got. When we reach this temperature, which is about 100 Kelvin, which is not that cold, it's close to the temperature of liquid nitrogen. It's close to the temperature of an industrial freezer. Well, that's a weird thing flying around there. So it's a reachable normal temperature. Above that temperature, the heat capacity goes up. It takes more heat to heat up my molecule by the same amount. So what's happening? Well, the heat is now going into rotational levels of the hydrogen as well as translational levels. And the rotational levels we can't see as heat because the heat is just the kinetic energy, the random kinetic energy of our hydrogen. So some of the energy is now going into something which is not counted, which we can't measure with a thermometer, and so we put in more energy per unit thermal increase. When we get to about 1000 Kelvin, which again, on the other side, it's a hot temperature, but it's not super hot. It's colder than most flames. It's hotter than most places we can survive, but it's also considerably colder than the temperature of molten steel, for example, or forging temperature. So it's not a super high temperature. And at that temperature, we start to activate the vibrational levels as well. So here we have another step, because some of our energy is going into increasing the vibrational levels, and that energy we cannot see when we measure the temperature, so we have to put in more energy to get the same change in temperature. So that is a real physical effect, and it relates to what we had last time, the theme that we had last time. It also relates to spectroscopy, because we can see that if we're measuring translational things, we will always see not the ground state. If we're measuring rotational levels, depending on the temperature and depending on the molecule, we can cool it down to make them less. We're unlikely to get cold enough unless we put a lot of effort in to turn them off, but it is physically possible. If we make it really cold, we can do it. So if we are interested in vibrational levels, most of the time we will be in the ground state because we're not hot enough. For some molecules, we might have some in the first excited state, but we're unlikely to get much further than that thermally, unless we have a very hot thing, in which case we will have vibrational levels active as well. So those are what we would expect to see in normal temperatures, so that can relate back to our spectroscopy. So this is fluorescence, a typical fluorescence drawing, where we have light coming in. It excites our electron, in this case, to an excited state. It decays non-radiatively to the lowest excited state, and that's because of the overlap between the 0 and the 0 states is very poor. Remember that. So we typically excite to some non-zero excited state. It typically relaxes by hitting stuff unless we're in low concentration gas phase, but if it's in liquid or solid state, it's very likely to hit something. Then it will decay, and it can't decay from the 0 to the 0 state for the same reason we couldn't excite it from the 0 to the 0 state. So it decays to an excited state, a non-zero excited state, and emits a lower energy, longer wavelength photon. But what happens if it wasn't at the ground state to start with? So in this case, our molecule starts in the second excited state. It's irradiated with a photon here, goes up to the ground state because we've chosen the wavelength to do so, and it can do that because it's not a 0 to 0 transition, so it's fine. And then it's in the ground state, so it has nowhere to relax to, and now it falls back down, but it doesn't have to fall back down to the same state it was in before and give out the same light that it gave out. It can fall back down to a lower energy level, which gives out a higher energy photon than came in. This is obviously unusual, but it will result in our material actually losing energy by having light coming in and light going out. So we get more energy out than we put in. Isn't that cool? If we consider a classical Raman picture, we would see that we're exciting our electron or our energy to a virtual state, which doesn't really exist. It decays immediately, and for the transition, most of them decay immediately back down to where they were before, but the ones that we measure go down to a different level. If they start at the ground level, they have to go to an excited state, and those are the Raman photons, which we measure the change in energy or the change in wavelength, however we want to produce it, and that's called the Raman Shift, which is what we present our spectrum in. So if we have this is a normal Raman, Stokes Raman, where we're putting energy into our molecule, our light comes out redder than before with less energy. But there's nothing to stop a molecule that starts in an excited state. So this is the one in the second excited state because it's then an analogy to the last example. It gets hit by a photon. The virtual level doesn't exist anyway, so it's going to move up and down with the wavelength of this and the energy level of our molecule. So that doesn't matter. If we excite to a virtual level and come back down again, we get more energy out than we had before. So we get a Raman shift. We get a Raman shift in the opposite direction, in the blue direction. So if we measure a Raman spectrum and we take our incoming light as the 0, there will be a Raman spectrum on the low energy side, and there will be another Raman spectrum on the high energy side. This will be much weaker because there aren't that many molecules in the excited state to start with, particularly considering what we just had before with temperature. So the population of these excited levels will be comparatively low, unless we're looking at rotational levels, in which case there will be some, unless we're at very low temperature. Both of these methods can be used as a kind of thermometer, because the amount that go out and give us energy out compared to the amount that go out and take energy in is related to the population of this energy level and this energy level, which are determined purely by quantum mechanics and the temperature. There is no other variable. So we can get a direct measure of temperature of that molecule in that place by measuring a Raman or a fluorescence spectrum, although fluorescence is slightly harder. Raman is better. If we consider an infrared spectrum, we can also see that because we are usually at the temperature where rotational levels are active, then we would expect our spectrum to consist of transitions of different rotational levels plus the vibrational level. That is what normally happens. We normally see rotational vibrational spectra, and that can be used to get more information about the molecule, particularly in the gas phase, because rotation is much better and purer in the gas phase because it's just rotating on its own and not hitting anything. But in any case, our lines that we get from the spectrum will be broadened by rotational energy levels because they will be populated at normal temperatures. So unless we go to very low temperatures, we are unlikely to get a very neat spectrum. We're likely to get lots of narrow rotational bands close to each other, which typically our spectrometer will not resolve, so we'll just get one wide band, which is what we see in infrared. So to sum up, we would typically see very low populations of molecules in excited states unless we're looking at rotational excited states or very high temperatures. We can see, however, small effects in things like fluorescence, where our excitation band overlaps with our emission band, and it is nominally possible to give out more energy than we put in, because we can excite up here and we still get the same emission band out, because it's not related. We still go up to the same excited state. It's just we're going up from an excited state. If we try to measure that, it's obviously lower. The emission is lower or the absorption is lower, but it still exists, and we can get an information about temperature from that if we need to. It's not very good information if it's low intensity, but if we have a lot of fluorescence centers, so a lot of color in our sample, we can get the information out. If we measure Raman, we get both Stokes bands, which are the ones where we're putting energy in, net, on anti-Stokes bands where we're getting energy out. It's effectively an emission spectrum for infrared. In infrared, we typically see rotation bands inside our vibrational bands, and that broadens our spectrum. There is a quantum mechanical rule, which I try to avoid in this course, but I have to mention it right now, that says you cannot have zero transition. So you always have 1 unit of rotational energy change when you excite in infrared. And so the zero change band is not there, it's invisible. In between there are up and down bands, so we typically see 2 lobes of an infrared spectrum in the gas phase where the rotational parts are well resolved. In the liquid phase, they're not. In the liquid phase, we tend to see just a broader spectrum, but it's broadened anyway due to a whole variety of other effects. So if we are bringing other groups of the polar up to our bond, or its orientation is changing, then we have a whole lot of different possibilities for the bond strength, and so our bond has different amounts of energies that it can absorb, which means that our peak is broad. So we're unlikely to see that in liquid phase or in solid phase. In laser cooling, we deliberately put in a very narrow band of light at 1 energy to excite, and we extract the energy out by exciting it up to a 0 excited state and then letting it fall back down to the ground state. And if we choose it well, we end up with net less energy in our molecule when it's absorbed the laser and given out light, and that can cool the sample. It's only possible in specific cases, but it is interesting. So now we're going to go on to the next topic, so I'm going to close this video for today.